Okay, so let's continue looking at geometry. So as I said, it's kind of the place where the Greeks sort of parked all their mathematics, and so it's where they were kind of doing algebra. And that's actually kind of like a big debate about, is this real algebra? So, you get mathematical historians arguing, well, the ancient Egyptians did algebra. No, they didn't. The Babylonians did algebra. No, they didn't. That's the kind of sort of thing. The person who's really, really rock solid considered to be doing algebra is Diophantus, who we'll get to. He's a Hellenistic mathematician around 100 CE. And is someone here going to be talking about him? So Diophantus, from where we get Diophantine equations from. So anyway, so we're looking at problems of how they did geometry. Okay, and so we're going to look at a really spectacular piece of work that comes from ancient times, Archimedes' construction of the Heptagon. So in an earlier lecture, I remember talking about constructing various figures, and that in the late 18th century, it was finally proved that the Greeks' method of construction of using straight edge and compass could not construct everything. So, for example, they could only construct regular polygons of a certain number. So it could be any factor of 2, and it could have a factor of a Fermat prime. So that meant that you can construct 3-sided figure, 4-sided, 5-sided, 6-sided, 8-sided, 10-sided, but you couldn't. They didn't figure out how to construct a 7-sided or a 9-sided figure, and this was actually proved then that was wrong. And some of the authors also talked about other classical problems, which were like trisecting angles, the quadrature of the circle, and the duplication of the cube. So these were problems that we look at them and think, why is that a problem? So for example, the duplication of the cube means that you have to construct the length cube root of 2. And to us, that's a kind of a strange thing, because cube root of 2, we think of the cube root of 2 as, the number that when you cube it, you get 2. And we can put it in our calculator, and we can come up with the cube root of 2 to as many decimal places as we like. Okay? But for them, they wanted to actually construct a length of cube root of 2. And you can't do it on with straight edge and compass, but it's very easy to do with conic sections, right? Because you can take the cube root of anything with a conic section. So, for example, if we just have the hyperbola A on x, right? And we have the parabola y equals x squared, okay? And we just see where they intersect. They're going to intersect where a over x equals x squared. So a equals x cubed, okay? And so when we, put it in our Cartesian coordinates, we've got our hyperbola here, we've got our parabola here. There we go. That length there is the cube root of a, and this length here is a to the 2/3. Simple as anything, right? This is, yeah, you almost think I've done nothing. But the Greeks couldn't do this, right? They had to try and do lines and circles. stop the share. Where's my? Oh, there we go. Oh, okay, so they wanted to do various things and they couldn't. So naturally what you try and do is you come up with new things to try and solve the problem. I mean, you have your problem, you can't do it one way, you try and find another way to do it. And so there are certain problems that you can do with straight edge and compass, but this is kind of like a static geometry. Basically, what you do is you have two things and you make a third thing. So, for example, I give you a point C and a point V. I can draw a circle then with a compass centered at C, V being on the boundary. I can do a straight line, C through V, and that gives me a diameter. I can take this point C and this line, and I can look at its perpendicular, and so that gives me that line there. Then I can do the same thing. I can make this line and this line the same length as that, and then I can draw this point to that. I made myself a little rectangle. I can then join that point to that point, gives me a straight line. These two lines then give me a point. So you see what it is. It's like it's constructing it. Two things that are fixed give me a third thing that's fixed. Okay, and then over here, I put, I've got 2 points A and V, so I look at the circle that makes. I intersect that circle with this diameter here, that gives me a point D. I then take the compass and put it at V and go to D, and I make a circle, and I get the points W and X on the circle, and this happens to be 1/5 of the circle, and we can make a pentagon now. Okay, so this is all straight edge and compass, a static geometry. Okay, so what they came up with then to give them extra stuff to be able to solve problems is what they called, I don't know how to pronounce that word, neusis or neusis, something like that, which we call verging constructions or moving constructions. So what you do is you start off with a circle and you have a hexagon in it. A hexagon is a perfectly constructible figure, so you can do that. And then you take the tangent lines at these points here, and where they intersect, that gives you another circle, and that gives you a set of circles. You make it the same diameter, so you haven't done anything radical now, but now what you do is you now, please, you now drag the circle back, and these arms here move down until they intersect those points over here. And when you do, lo and behold, this angle here turns out to be 40 degrees, which is 1/9 of 360 degrees. So you can use then that to construct a 9-sided figure. Okay, so it was this thing of moving the circle, which is different from what we saw before. So this is a trick of Archimedes. He's a very tricky guy. Another trick that he did was he came up with a spiral. So if you think about it, a spiral is kind of like a moving thing, right? Because how do you define a spiral? You've got like a, the camera. You get kind of like a radial arc, and you rotate that around, but as it rotates, you extend it further and further along. So in polar coordinates, it's r equals theta. Okay? Now, this is great, right? Because we know that in constructive geometry, you can subdivide length as much as you like, but you can only bisect angles. With the circle, r equals theta, you've got something which now translates angles and lengths. Okay, and so since you can arbitrarily subdivide a length, that means with a spiral you can arbitrarily subdivide an angle. Wow, very simple, you know. That's, you know, Archimedes, what a brain. Okay. So all kinds of things like that. So a typical verging construction might be something like that. You know, you've got, say you've got a circle here. You've got a diameter here, and you've got some length AB, and you want to make a length, a segment AB, such that the endpoints touch the circle and the diameter, but it has to go through some point P. So you've got to get this AB, and you've got to sort of settle it in there to go like that. You can't do that with straight edge and compass. It's a moving construction. So these are the types of constructions that they use to come up with to solve the problems that they couldn't solve with before. Okay, so let's have a look at how Archimedes made a heptagon. So first off, he started with a square, and he puts in a diagonal. All very straightforward. Okay, that's in Euclid book 3 and 4, How to Make a Square. Oops. Okay, here's where things get tricky. Okay, so now you put a straight edge on D, and you make a line going this way, and it's going to cross the diagonal here, and it's going to cross the line this side here at E, and it's going to meet up an extension of BA at some point Z. And so what you want to do is you want to position this line such that this area of this triangle equals the area of this triangle. Okay. So this is a nuesis. This is a moving construction. If you think about it, such a point Z has to exist. And we can see that by some sort of like continuity argument. Because what happens if Z is really close to A? How do the two triangles compare? Right, this one here is really tiny, and this one is almost like a quarter of the square. Now, as Z goes further and further, it goes off to infinity, what happens to this triangle? It gets bigger and bigger and bigger, and we can make it as big as we want. And this triangle here gets smaller and smaller. And eventually infinity goes to 0. So one triangle is going up in size, the other triangle is going down in size. There has to be some point at which they meet. Okay. But that's just an existence argument. It's not really showing how you actually do this. So this was a paper of Archimedes that's only known from the Arabic translation. So the Arabic scholars had a copy of this. They had it at Baghdad, and they were just sort of stunned by it because they can see. So as we'll see later on, the construction is super elegant, very, very classy. But it's just like, how do we do this? And so one commentator, I think from the 9th century, Abu al-Jad said, perhaps its execution is more difficult and its proof more remote than for which it serves as a premise. So it's just like, oh, how do we do this? But after you do that, the rest is just construction. Okay? you draw a line through T, which is parallel to the sides. And then this means we have constructed a line segment BZ, which is cut at A and K. And Archimedes proves three things: that the three sides, the three subsegments can form a triangle. Or what does that, how can that be? Well, that can be as long as the biggest length is not bigger than the sum of the previous two, right? Because it has to satisfy the triangle inequality. And BA times BK equals AZ squared, and KZ times KA times KB squared. So remember what we mean by that. We mean that the rectangle whose sides are BA and BK has that same area as the square on AZ. And similarly, the rectangle whose sides are KZ and KA has the same area as the square on KB. Okay. Then you take your line segment, since the sides can form a triangle, you do form a triangle, and so this length is equal to this length, and HA is equal to AZ. And we're done now. Because we've got 3 points, BHZ, 3 points make a circle. That's another Euclidean construction. Given 3 points, you can come up with a circle. And the arc BH is 1/7 of the circle. And once you've done that, you can then make a heptagon, because then you can draw a line B to H, get out your compass. You can then make an arc length over here, draw there, and then with your compass, you just go around making 1/7 of the circle, and there's your heptagon. Okay, pretty impressive. And this impressed the people. Okay. Now, what do we think about this? Okay. So, for us, the problem of constructing a heptagon is really not what we would, not a math problem that we deal with. Okay. So, in modern terms, perhaps the way that we would think about it is that we're finding sine of 2 pi on 7. That might be the modern equivalent of constructing the heptagon. So instead of doing a geometric construction, it's just finding this trig value. That would be what it is in more kind of modern terms, and finding sine of 2 pi on 7 or cos of 2 pi on 7. We've got trig tables for that. So it's not really, and the reason I say a trig value of 2 pi on 7, because if you know the value of sine 2 pi on 7, what can you do? You can then make triangles, and you can make a triangle like this. Here's 2 pi on 7. If this is 1, you can figure out the length of that, and that's the side of the 9-sided figure. And then once you've got one of them, you get 9. That's like a piece of pie. You put 9 of them together, and there's your nonagon. So that'd kind of be more like how we might think of the problem. But for the classical Greek, and later on, this kind of influenced mathematics for a long, long time. There was like a hierarchy of proof. The best proof was straight edge and compass, because that's Euclid. And Euclid is the bedrock of mathematics, and it was for a long, long time. So you can prove something with straight edge and compass, it is 110% true. Okay. Second, if you couldn't solve it by straight edge and compass, solve it by conic sections. Conic sections wasn't Euclid, but it was Apollonius, right? And Apollonius had done his conic sections book. It's difficult, it's hard, but we have faith in Apollonius. He's one of the three pillars, okay? So conic sections, you know, if this is 100%, this is like 95%, okay? But conic sections is still a nuisance. I'm saying it right. I'm probably saying it differently every time I say it. Because how does a conic section come about, right? Because we've got a cone with a plane. And so the way that I like to think of conic sections is it's kind of like you've got a cone, but a cone is just a device to have varying circles, right? So you have circles at each level of the cone, and at each level you have a different radius of the circle. So it's a way, conic sections is kind of a way I like to think of it as having something with variable circle size. And that's the moving geometry part. So, but of course, the way that you think of it, of conic sections is, you know, whatever symptoms you have. So for us, it's the equations, but for the classical Greeks, it was those relations about application or application with excess or application with defect. Okay. And then third is any other way you can do it, okay? So if you can come up with something that'll solve the problem, then fine. But it's only there as a placeholder until a better method can come along. Okay, and so what we're going to be looking at next, I only wanted to talk for around like half an hour today, so this is kind of last slide. We're going to look at Islamic mathematician Abu Sal al-Kuhi. He was a mountain man. We can tell he's a mountain man because of his name. Ku is Persian for mountain. So he came from the mountainous region, which is just south of the Caspian Sea. He's a very interesting guy, late 10th century. He started off life as a juggler. Like in the marketplace, he juggled glass bottles. And so he became interested in Archimedes, of course, because Archimedes, one of the things Archimedes wrote about was the centers of gravity. And if you're a juggler, juggling glass bottles, you're really concerned with. So supposedly he started reading Archimedes for that and eventually became a mathematician. So it's an interesting career choice. And so he looked at this problem and he moved it from 3 to 2. So he came up with a way of using conic sections instead of Archimedes' nuisance of the 2 triangles. He came up with a way of using conic sections to solve the problem. And that's what we're going to be looking at. And so he improved the proof. He improved Archimedes, which is a really amazing achievement. But also, it's kind of important if we look at it from kind of like a big picture kind of thing about what we like to do in mathematics. So in science and mathematics, we love unification. Okay, so we really don't like, you know, jagged topics kind of like all over the place. We like to kind of bring them together, and we like some sort of unified approach to things. And so Abu Sal's work can be looked in that respect of, like, he took this glittering gem of a proof of Archimedes and he brought in conic sections to it and showed how it fitted in with that. And so it kind of made this thing which was kind of like an outlier, it kind of brought it into the the mainstream of mathematics. And that's kind of like always an impulse that works on people doing mathematics. Okay, so when we look at it, it's going to be using the method of analysis and synthesis, which is the really classical way of proving things. Supposedly it goes back to Plato. And it's this. So you want to prove something. So what does a proof consist of? A proof consists of hypotheses and conclusion. Okay? In analysis, what you do is you take your conclusion and you reduce it to the hypotheses. And then in synthesis, you go the other way. The synthesis is what we regard as the proof. You then take your what you've got your hypotheses, and you go back to come to the conclusion. And so that was the way classically you're supposed to prove these things. So what we're going to look at next week is Abu Sal's analysis, where he starts off with a heptagon, and then he reduces it through various things to two conic sections, the intersection of two conic sections. And then you run that backwards, and then you get, in the synthesis, you get the construction then of the heptagon. I think that's what I wanted to say today. Okay. So how is this kind of like from time-wise? I'm thinking like with my lectures and the lectures online, is that I'm thinking it's I'm roughly doing the right amount. Again, if things get too extreme, please inform me.